All right, so that concludes my discussion of different parameter updates, decay your learning rates. We're not going to look into LBFGS in this class. Okay? There's a question in the very back.
Yeah, so we talked about why it's good to decay your learning rates, but also why the additive suffers because it decays your gradient that can update.
So I'm not sure if I fully understood your question. You're asking about, so Adagrad, for example, it automatically decays your learning rate over time. So would you use also learning rate decay if you're using Adagrad? So usually you see learning rate decay very common when you do SGD or SGD momentum. I actually am not sure if you'd use it with Adagrad or Atom.
I've used your learning rate decay with Atom before. It tends to help a little bit, but it kind of breaks some of the theory. But it does help sometimes.
Yeah, it's not. Yeah, yeah. So not a very good answer there. You can certainly do it, but maybe Atom is not. Like Atom will not just monotonically make your learning rate 0 at the end, right? Because it's a leaky gradient. But if you used Adagrad, then certainly decaying the learning rate probably does not make sense because it's decayed automatically to 0 in the end. All right, cool. OK, so we're going to go into model ensembles. I just very briefly like to talk about it because it's quite simple. Turns out that if you train multiple independent models on your training data, instead of just a single one, and then you average their results at test time, you always get 2% extra performance. Okay, so this is not really a theoretical result here. It's kind of like an Andre result, but just like in practice, basically, this is like a good thing to do. Almost always works better. The downside, of course, is now you have to have all these different independent models, and you need to do forward and forward passes of all of them, and you need to have trained all of them. So that's not ideal because you have a linear slowdown test time with the number of models in your ensemble. And so there are some tips and tricks for using ensembles, but kind of faking it a bit. So one approach, for example, is as you're training your neural network, you have all these different checkpoints. Usually you're saving them every single epoch. You save a checkpoint and you figure out what was your validation performance. So one thing you can do, for example, it turns out to actually give slight boosts sometimes, is you just take some different checkpoints of your model and you do an ensemble over those. That actually turns out to sometimes improve things a bit. And so that way you don't have to train 7 independent models. You just trained 1, but you ensemble some different checkpoints. Related to that, there's a trick of for test. OK, so what's happening here, this is your 4 steps that we've seen before. I'm keeping another set of parameters here, x test. And this x test is a running sum, exponentially decaying, of my actual parameter vector x. And when I use x test in validation or test data, it turns out that this almost always performs slightly better than using x alone. Okay? And so this is kind of doing like a small, like weighted ensemble of previous few parameter vectors. It's kind of difficult to interpret actually, but basically one way to interpret it, one way I can hand wave about why this is actually a good thing to do, is think about optimizing your bowl function, and you're stepping too much around your minimum, then actually taking the average of all those steps gets you closer to the minimum. Okay, so that's the hand waving I can do for why this actually ends up working slightly better. So that's model ensembles. I had to discuss model ensembles because we're going to look into dropout. And this is a very important technique that you will be using and implementing and so on. So the idea for dropout is very interesting. What you do with dropout is as you're doing a forward pass of your neural network, you will randomly set some neurons to 0 in the forward pass. Okay? So just to clarify, what you will do is as you're doing a forward pass of your data x, you're computing, say in this function, your first hidden layer is the nonlinearity of w1 times x plus b1. So that's the activations of the first hidden layer. And then I will compute here a mask of binary numbers, either 0 or 1, based on whether or not numbers between 0 and 1 are smaller than p, which we here see is 0.5. So this u1 is a binary mask of 0s and 1s, half and half. And then we multiply that onto our hidden activations, effectively dropping half of them. So we've computed all the activations h1, the hidden layer, and then we drop half the units at random. And then we do second, and then we drop half of them at random. Okay? And of course, this is only the forward pass. The backward pass has to be appropriately adjusted as well. So these drops have to be also back propagated through. So remember to do that when you implement dropout. So it's not only in the forward pass you drop, but in the backward pass you have to back propagate through multiplying by u2 and by u1. So you kill gradients basically in places where you've dropped a unit. Okay, so you might be thinking when I showed you this for the first time, how does this make any sense at all? And how is this a good idea? Why would you want to compute your neurons and then set them at random to 0? How does that make any sense whatsoever? So I don't know. Let's. What do you guys think? Go ahead.
Would it prevent overfitting?
Would it prevent overfitting? In what sense?
It could probably give, instead of getting some neurons, I guess it would make it, force it to be more like use over time.
Okay. You're roughly getting the right intuition. So you're saying it will prevent overfitting because if I'm only using half of my network, then roughly I have like smaller capacity. I'm only using half of my network at any one time. And with smaller networks, there's only like, there's only so much I can do with half a network than as a full network. So it's kind of like a control of your variance in terms of what you can represent. Go ahead.
That is the same thing. A variance of it sees a lot of different variants in the input.
Yep. Okay. I would like to be slightly careful with the terms like bias, variance, trade-off, and so on. We're not going into that too much. But yeah, basically, you have a smaller model. It's harder to overfit. Go ahead.
It's like having many ensembles of neural networks.
Okay, you're saying it's like having many ensembles of different neural networks. We're going to go into that point in a bit. Go ahead.
It's forcing all the individual neurons to be useful and not just allow one particular one to be useful, because when that gets dropped off, you get a big negative result.
Okay, so you're saying that it's forcing all the neurons to be useful, because if one of them gets dropped out, then if that one was the only one that was used upstairs, okay, I have a better way of rephrasing that point in my next slide. Let's look at a particular example instead of hand waving, okay? Suppose that we are trying to compute the CAT score in a neural network, okay? And the idea here is that you have all these different units, and what dropout is doing is it's forcing, there are many ways to look at dropout, but one of them is it's forcing your code, your representation for what the image was about, to be redundant. Because you need that redundancy because you're about to, in a way that you can't control, get half of your network dropped off. And so you need to base your CAT score on many more features if you're going to correctly compute the CAT score, because any one of them, you can't rely on it because it might be dropped. And so that's one way to look at it. So in this case, we can still classify CAT score properly, even if we don't have access to whether or not it's furry or mischievous and so on. So that's one interpretation of dropout. Okay? Another interpretation of dropout is, as was mentioned, in terms of an ensemble. So dropout is effectively, can be looked at as training a large ensemble of models that are basically sub-networks of this one large network, but they kind of share parameters in a weird way. So to understand this, you have to notice the following. If we do a forward pass and we randomly drop off some of the units, then in backward pass, think about what happens with the gradient, right? So suppose we've randomly dropped off these units. In a backward pass, we're backpropagating through the masks that were induced by the dropout. So in particular, only the neurons that were used in the forward pass will actually be updated or have any gradients flowing through them. Because any neuron that was shut off to 0, no gradient will flow through it, and its weights to its previous layer will not be updated. So effectively, any neuron that was dropped out, its connections to the previous layer will not be updated, and it's as if it wasn't there. So really, with the dropout masks, you're subsampling a part of your neural network, and you're only training that neural network on that single example that you have at that point in time. So each binary mask is one model and gets trained on only one data point.
I'm not sure what you said.
Okay. I can try to repeat that. It came from somewhere here. I'm on to you guys. Okay. But do people actually understand this, or nods, or? Okay. So when you drop a unit, you drop a neuron. I wish I had the example of the neuron, right? But if I drop its value, I multiply its output by 0, then its effect on the loss function, there's no effect, right? So its gradient will be 0 because its value was not used in computing the loss. And so its weights will not get an update. And so it's as if we've subsampled a part of the network and we only train that single data point that currently came to the network, we only train on it. And every time we do a forward pass, we've subsampled a different part of your neural network, but they all share parameters. So it's kind of like a weird ensemble of lots of different models, all trained on one data point, but they all share parameters. So that's kind of roughly the idea here. Does that make sense? Okay, cool. Go ahead, question?
What percentage of the neurons in a network get dropped out?
Usually, say 50% is a very rough approximation you can use.
And then do your weight arrays, do they still stay the same size, or are there ways to scale down the weight arrays in a way?
Yeah, the weight array is the same size. So in this forward pass, you'll notice we actually compute all the neurons, H. We compute them just as we did before. All of the neurons get computed, but then half of the values will get dropped to 0. So nothing changes there.
Just scale it
Oops, sorry.
times 2 or something like that.
Oh, yeah, so we'll see that in a bit. Go ahead.
Won't you be making the matrix sparse so you can use a bunch of sparse matrix optimizations when you do the calculations?
Would you be making the matrix sparse? So can you take advantage of some sparse matrix computations? So instead of computing all the H's, you want to only compute the neurons that are not being dropped. And in that case, you want to do sparse updates.
Yeah.
So you could in theory, but I don't think that's done usually in practice. We don't worry about it too much.
So I guess it would depend on what neurons get dropped out, right? So, but like iterating over all combinations is a bad like runtime.
Mm-hmm.
So how do you choose which ones to drop?
Oh, I see. So in every single forward pass, we sample these, right? We sample the mask at every single forward pass. And so you always get a different like subnetwork that you're training. So every single iteration, we get a mini batch, we sample our noise pattern for what we're going to drop out, and we do a forward and backward pass and update the gradient. And we keep iterating this over and over again.
But is there like a potential algorithm to like precisely choose the good?
Oh, I see. So your question is, can we like somehow cleverly choose the binary mask in like a way that best optimizes the model or something like that? Not really. I don't think that's done or anyone has looked into it too much. Go ahead.
For test purposes, we don't do the dropout.
Sorry?
Do we do the dropout for test purposes?
Yes, so I'm going to get into that in one slide. In the next slide, we're going to look at test time. I'll take up one last question. Go ahead.
Have you tried do different masks, different CP on different layer? And another question is, is there you try like dropout on weight instead of dropout?
So 2 questions. One is, can you use dropout to different amounts in different layers? You can. There's nothing stopping you. It's intuitively, you want to apply stronger dropout if you need more regularization. So if there's a layer that has a huge amount of parameters, we'll see that in ComNets in one example, you want to apply stronger dropout there. Conversely, there might be some layers that we'll see with convolutional networks. Early on, the convolutional layers are very small. You don't usually apply as much dropout there. So it's quite common, for example, in the convolutional network, and we'll go into this in a bit, you start off with low dropout, and then you scale that up over time. So the answer to that is yes. And I forgot your second question. What was it? Oh, can you, instead of units, drop out just individual weights? You can, and that's called something called drop connect. We won't go into it too much in this class. But there's a way to do that as well. OK. Now, at test time, ideally what you want to do is we've introduced all this noise, right, into the forward pass. And so what we'd like to do now at test time is we'd like to integrate out all that noise. And a Monte Carlo approximation to that would be something like you have a test image that you'd like to classify. You can do many forward passes with many different settings of your binary masks, and you're only using the subnetworks. And then you can average across all those probability distributions. So that would be great, but unfortunately, it's not very efficient. So it turns out that you can actually approximate this process to some degree, as Jeff Hinton pointed out when he first introduced dropout. And the way we'll do this, intuitively, you want to take advantage of all your neurons. You don't want to be dropping them out at random. So we're going to try to come up with a way where we can leave all the neurons turned on, so do no dropout in a forward pass on a test image. But we have to actually be careful with how we do this. So in a forward pass for test images, we're not going to drop any units, but we have to be careful with something. Basically, one way to get at what the issue is suppose that this was a neuron, and it's got 2 inputs. And suppose that with all these inputs present at test time, so we're not dropping units. So we're at test time. These 2 have some activations. And the output of this neuron gets computed to be some value x. You have to compare this value of x to what the neuron's output would be during training time in expectation. Okay, because in training time, this dropout masks vary randomly, and so there's many different cases that could have happened. And in those cases, the outputs of this neuron would be possibly in a different scale, and you have to worry about this. So let me show you exactly what this means, I think. So during test, this neuron computes, say there's no nonlinearity, we're only looking at a linear neuron. During test, this activation becomes W0, which is the weight here, times x, plus W1 times y. Okay, so that's what we want to compute at test time. And the reason we have to be careful is that during training time, the expected output of A in this particular case would have been quite different. So we have 4 possibilities. We could have dropped one or the other or both or none. So in those 4 possibilities, we would have computed different values. And if you actually crunch through this math, you'll see that when you reduce it, you end up with 1/2 of W0x plus W1 times Y. So in expectation at training time, the output of this neuron was actually 1/2 of what it is at test time. Okay? And so when you want to use all the neurons at test time, you have to compensate for this additional 1/2. And that 1/2, by the way, is coming from the fact that we've dropped units with probability of 1/2. And so that's why this ends up being 1/2. And so with probability 0.5, all inputs in a forward pass. So basically, if we did not do this, then we end up having too large of an output compared to what we had in expectation during training time. And your output distribution would change. And basically, things in the neural network would break because they're not used to seeing such large outputs from all the neurons. And so you have to compensate for that, and you have to squish down. So now you're using all your things instead of just half of the things. But you have to squish down the activations to get back to recover your expected output. Okay? This is actually a tricky point. By the way, I think I was told once a story that when Jeff Hinton came up with dropout, in the beginning, he actually didn't fully come up with this part. So he tried dropout, and it didn't work. And actually, the reason it didn't work is he missed out on this tricky point, actually, admittedly. And so you have to scale your activations at test time down because of this effect, and then everything works much better. So at test time, just to show you what this looks like, we basically compute these neural nets as normal. So we compute the first hidden layer, second hidden layer. But now at test time, we have to multiply by p. So for example, if p is 1/2, we're dropping out with 1/2 probability. Then we're scaling down the activation so that the expected output now is the same as expected output in the training time. And so at this time, you actually recover full dropout, and the expected outputs are matching. And this actually works really well. Go ahead.
At training time, 1/4 of the time, I will actually have the same problem, right? Because both neurons will be active. And so I just don't do the scaling. Is that a problem for training? Does it slow down training?
So in training, we're half the time dropping these inputs. And so you end up with some expected output from this neuron. I don't think there's an issue at training time, basically. It's just the discrepancy between train and test. Like if you're using all your neurons instead of dropping them, there's a discrepancy. So either you can correct it at test time, or you can use what we call inverted dropout, which I'll show you in a bit. So let me just get to that in a bit. So dropout summary, if you want to use dropout, drop your units with probability of, with keeping a probability of p. And then at test time, don't forget to scale them. So if you do this, your neural networks will work better. Okay? And don't forget to also backpropagate the masks, which I'm not showing here. An inverted dropout, by the way, is to take care of this discrepancy between the train and test distribution in a slightly different way. In particular, what we'll do is we're changing this step here. So before U1 was a binary mask of zeros and ones. What we're now going to do is we're going to do the scaling here at training time. So we're going to scale down the activations at training time, or rather scale them up, because if p is 0.5, then we're boosting activations at training time by 1/2. And then at test time, we can leave our code untouched. Right? So we're doing the boosting of the activations at train time. We're making everything artificially greater by 2x. And then at test time, we're supposed to half. But now we're just going to recover the clean expressions because we've done the scaling at training time. So now you'll be properly calibrated in expectations between the train and test of every neuron in the network. Okay? So that's dropout. So use inverted dropout. That's the most common one to use in practice. So in effect, it really comes down to a few lines. And then the backward pass changes a bit. But the networks almost always work better with this. Go ahead. Unless you're severely underfitting. Go ahead.
Would you sort of make the approximation that the neurons are going to see the expected value of like the weights after dropout? Does that depend on you having a linear response in your activation function?
Thank you for the question. Does that depend on you having a linear response activation function? It does. So once you have nonlinearities in there, then these expectations aren't actually exact. And that's why this is an, as I mentioned here, approximation. It's an approximation to evaluating the full ensemble. And one of the reasons it's an approximation is because once you actually have nonlinearities in the picture, then these expected outputs are all kind of screwed up because of the nonlinear effects on top of these. So yeah, that's a good question. Thank you for pointing that out. Go ahead.
Since it's not linear, like inverted dropout and dropout are not equivalent in terms of the final model.
I see. You're saying that the inverted dropout and dropout are not equivalent. So doing inverted dropout or not is not equivalent because of the nonlinearities. I'd have to think about it. Maybe you're right. Yeah, maybe you're right. Yeah. Yeah. Good.
So in the inverted dropout, why
Yeah.
is it that you're dividing by p rather than you can imagine instead dividing by the mean and the mass?
So p here is 0.5, right? So with probability of 0.5, we're dropping.
You've selected either the number you've selected is some binomial, right? So you may have selected a really small network or a really big network, and you can imagine that.
I see. So sometimes you have more dropped and less dropped, and you have an entire distribution. Like in some forward passes, you'll have fewer neurons than half, or more neurons than half. But I think all of this is just about expectations.
Okay.
In expectation, you're dropping a half, and so that's the correct thing to use, even though there's some randomness on exactly the amount that actually end up being dropped. Okay, great. Oh yeah, this is a placeholder slide to tell you guys a fun story about dropout. So I was in a deep learning summer school in 2012. And Jeff Hinton was, for the first time, or at least the first time I saw it, presenting dropout. And so he's basically just saying, OK, set your neurons to 0 at random, and at test time, just boost the activations. And this always works better. And we're like, wow, that's interesting. And so a friend of mine sitting next to me, he just pulled up his laptop right there. He SSH'd into his university machines, and he implemented right there during the talk. And by the time Jeff Hinton finished the talk, he was getting better results and getting actually state-of-the-art report like accuracies on his data set that he was working with. So that's the fastest I've seen someone go get an extra few boost percent. It was right there and then while Jeff Hinton was giving the talk. So I thought that was really funny. There's very few times that actually something like this happens. And so dropout is a great thing because it's one of those few advances that is very simple and it always works, just better. And there's very few of those kinds of tips and tricks that we've picked up. And I guess the question is, how many more simple things like dropout are there that just give you 2% boost always? So we don't know. OK. So I was going to go at this point into gradient checking. But I think I decided that I'm going to skip this because I'm tired of all the neural network. Like we've been talking about lots of details of training neural networks, and I think you guys are tired as well. And so I'm going to skip gradient checking because it's quite well described here in notes. So I encourage you to go through it. Gradient checking is kind of a tricky process. It takes a bit of time to appreciate all the difficulties with the process. And so just read through it. I don't think there's anything I can hand wave around to make it more interesting to you. And so I would encourage you to just check it out. Meanwhile, we're going to jump right ahead and go into convolutional networks and look at pictures. Okay? So convolutional neural networks look like this. This is a LeNet 5 from 1980, roughly. And so we're going to go into details of how convolutional neural networks work. And in this class, we're not actually going to do any of the low-level details. I'm just going to try to give you intuition about how this field came about, some of the historical context, and just convolutional networks in general. So if you'd like to talk about the history of convolutional networks, you have to go back to roughly 1960s to experiments of Hubel and Wiesel. So in particular, they were studying the visual cortex in a cat. And they were studying an early visual area in the cat brain as the cat was looking at patterns on the screen. And they ended up actually winning a Nobel Prize for this sometime later, for these experiments. And so I'd like to show you what these experiments looked like, just so they're really fun to look at. So I pulled up a YouTube video here. And so what's going on here is the cat is fixed in position, and we're recording from its cortex somewhere in the first visual area of processing, which is in the back of your brain, called V1. And now we're showing different light patterns to the cat, and we're recording and hearing the neurons fire for different stimuli. So let's look at how this experiment looked like. I don't know if you guys can hear. So nothing happens when it goes this way. And then he's going to make it go that way. OK. I don't know if you guys can hear it all the way back. OK. So this is one neuron in the V1 cortex. And through experiments like this, they basically figured out that there are these cells, and they seem to turn on for edges in a particular orientation. And they get excited about edges in one orientation. Any other orientation does not excite them. Okay. And so like this, through a long process, this is like a 10-minute video, so we're not going to go through it. But basically, for a long time, they experimented, and they came up with a model of how the visual cortex processes information in the brain. And so they found several things that ended up leading to their Nobel Prize. For example, they figured out that the cortex is arranged retinotopically, the visual cortex. And what that means is that, let's see, where's my pointer? Basically, nearby cells in the cortex, so this is cortical tissue unfolded. Nearby cells in your cortex are actually processing nearby areas in your visual field. So whatever is mapping onto your retina is processed nearby in your brain. This locality is preserved in your processing. And they also figured out that there was an entire hierarchy of these were what's called simple cells, and they responded to a particular orientation of an edge. And then there were all these other cells that had more complex responses. So for example, some cells would be turning off for a specific orientation, but were slightly translationally invariant. So they didn't care about the specific position of the edge, but they only cared about the orientation. And so they hypothesized through all of these experiments that the visual cortex has this kind of hierarchical organization where you end up with simple cells that are feeding to other cells called complex cells, and etc. And these cells are building on top of each other. And these simple cells in particular have these relatively local receptive fields, and then we're building up more and more complex kind of representations in the brain through successive layers of representation. And so these were experiments by Hubel and Wiesel, and of course they, some people are trying to reproduce this in computers and trying to model the visual cortex with code. And so one of the first examples of this was the neurocognitron from Fukushima, and he basically ended up setting up a layered architecture with these local receptive cells that basically, these are neurons that look at a small region of the input, and then he stacked up layers and layers of these. And so he had these simple cells and then complex cells, simple cells, complex cells, and this sandwich of simple and complex cells building up into a hierarchy. Now back then though, in 1980s, backpropagation was still not really around. And so Fukushima had an unsupervised learning procedure for training these networks with like a clustering scheme. But this was not backpropagated at the time, but it had this idea of successive layers, small cells building up on top of each other. And then Jan LeCun took these experiments further, and he kind of built on top of Fukushima's work, and he kept the rough architecture and layout. But what he did was actually train these networks with backpropagation. And so, for example, he trained different classifiers for digits or letters and so on, and so trained all of it with backprop. And they actually ended up using this in complex systems that read check, they read off like digits from postal mail service and so on. And so ComNets actually go back to quite a long time ago, to 1990s and so on, when Jan LeCun was using them back then, but they were quite small, okay? And so in 2012 is when the ComNet started to get quite a bit bigger. So this was the paper that I keep referring to from Alex Kruchevsky, Elias Atskever, and Jeff Hinton. They took all of ImageNet. ImageNet is a data set that comes actually from Feifei's lab, from our lab. So it's 1 million images with 1,000 classes, huge amount of data. You take this model, which is roughly 60 million parameters, and it's called an AlexNet, based on the first name of Alex Kruchevsky. These networks, we're going to see that they have names. So this is AlexNet, there's a VGGNet, a ZFNet, GoogleNet. There's several nets. So just like this one is Linet. And so we give them names. So this was AlexNet, and it was the one that actually outperformed by quite a bit all the other algorithms. What's interesting to note historically is the difference between AlexNet in 2012 and the Linet in 1990s. There's basically very, very little differences when you look at these two networks. This one used, I think, sigmoids or 10H probably, and this one used ReLU. And it was bigger and deeper, and it was trained on GPU, and it had more data. And that's basically it. That's the only, that's roughly the difference. And so really what we've done is we figured out better ways of course, initializing them, and it works better with batch norm, and ReLUs work much better. But other than that, it was just scaling up both the data and the compute. But for the most part, the architecture was quite similar. And we've done a few more tricks. Like, for example, they used big filters. We'll see that we use much smaller filters. We also now, this is only a few tens of layers. We now have 150 layer ComNets, so we've really just scaled this up quite a bit in some respects. But otherwise, the basic concept of how you process information is similar. Okay? So ComNets are now basically everywhere. So they can do all kinds of things like classify things, of course. They're very good at retrieval. So if you show them an image, they can retrieve other images like it. They can also do detection. So here they're detecting dogs or horses or people and so on. This might be used, for example, in self-driving cars. I'll have this on the next slide. They can also do semantic segmentation. So every single pixel is labeled, for example, as a person or a road or a tree or a sky or a building. So that's segmentation. So they're used in cars. For example, here's an NVIDIA Tegra, which is a small embedded GPU. We can run ComNets on these, and for example, this might be useful in a self-driving car where you can identify you can basically do perception of of things around you. ComNets are identifying faces. Probably if some of your friends are tagged on Facebook automatically, it's almost certainly, I would guess at this point, a ComNet. They're used on video classification on YouTube, identifying what's inside YouTube videos. They're used in, this is a project from Google that was very successful, where basically Google was really interested in taking Street View images and automatically reading out house numbers from them. Okay, and turns out this is a perfect task for a ComNet. So they had lots of human laborers annotate huge amounts of this data and then put a giant ComNet on it, and it ended up working almost as well as a human. And that's a theme that we'll see throughout, that this stuff works really, really well. They can estimate poses. They can play computer games. They detect all kinds of cancer or something like that in bioimages. They can read Chinese characters, recognize street signs. This is, I think, segmentation of neural tissue. They can also do things that are not visual. So for example, they can recognize speech. So ComNets have been used for speech processing. They've been used also for text documents. So you can feed text into ComNets as well. They've been used to recognize different types of galaxies. They've been used to, in recent Kaggle competition, to recognize different whales. So this is a particular whale. There was like 100 whales or something like that, and you have to just use a ComNet to recognize specific individual whales. So this whale, by the pattern of its white spots on its head, is a particular whale that the ComNet has to recognize. So it's amazing that that works at all. They're used on satellite images quite a bit because now there are several companies that have lots of satellite data. So this is all analyzed with large ComNets. In this case, it's finding roads, but you can also look at agriculture applications and so on. They can also do image captioning. So you might have seen some of these results, my work included as well, where you take images and you caption them with sentences instead of just a single category. And they can also be used for various artistic endeavors. So this is something called Deep Dream. And we're going to go into how this works. You'll actually implement it, I think, on your third assignment, maybe?
Hopefully. We'll
okay.
see.
Maybe you will implement this on your third assignment. You give it an image, and using ComNet, you can make it do weird stuff. In particular, you'll notice there are lots of hallucinations of dogs. And we're going to go into why dogs appear. It has to do with the fact that ImageNet, which is where these networks get trained, they have a lot of dogs. And so so these networks end up hallucinating dogs. It's kind of like they're used to some patterns, and then when you show them a different image, you can make them, put them in a loop with the image, and they'll hallucinate things. So we'll see how this works in a bit. I'm not going to explain the slide, but it looks cool. So you can imagine that a ComNet is probably involved somewhere. I also wanted to point out that what's interesting, there's this paper called Deep Neural Networks, Rival Representation of Primate IT Cortex for Core Visual Recognition. What they did here is they are basically looking at, I think this was a macaque monkey, and they're recording from the IT, from the IT cortex here. And they're recording the neural activations as a monkey is looking at images. And then they fed the same images to a convolutional neural network. And what they're trying to do is, from the convolutional neural network code, or from the population of neurons that is only a sparse population of neurons in the IT cortex, they're trying to perform a classification of some concepts. And what you see is that decoding from the IT cortex and classifying images is almost as good as using this neural network from 2013. So in terms of the information that's there about the image, you can do almost equal in performance for classification. Perhaps even more striking results here, where they were comparing, they fed a lot of images through the convolutional network, and they got this monkey to look at lots of images. And then you look at how these images are represented in the brain or in the ComNet. So these are two spaces of representation of how images are arranged in the space by the ComNet. And you can compare the similarity matrices and statistics, and you'll see that the IT cortex and the ComNets are basically very, very similar representation. There's a mapping between them. It almost seems like similar things are being computed. The way they arrange the visual space of different concepts and what's close and what's far is very, very remarkably similar to what you see in the brain. And so some people think that this is just some evidence that ComNets are doing something brain-like, and that is very interesting. So the only question that remains then in that case is, how do ComNets work? And we'll find out in the next class. So that's it. Okay.